Now let's take a look at those anomalies. For group 13, 3 or 13 or 6 or 16, those anomalies in the ionization energies as we proceed across the periodic table. So let's dig in and look a little bit closer. You notice that lithium with a value of 521, and then it's higher, 900, and then there's an oops right here for column 3 or 13, the boron column. And then the trend is restored higher again, 1400 higher still, and now there's an oops again right here in column 16 or 6. The trend is restored as we proceed across the chart. You'll see the same thing happen in all of the columns. Sodium to magnesium, oh, that's annoying, sodium to magnesium, and then there's an oops right here with aluminum. The trend is restored up to 780, 1050, and then an oops right here with sulfur, and the trend is restored again. What's going on here? Let's take a closer look. So as we've said, the general trend of increasing ionization energy would make you think, if you didn't realize there were some anomalies, would make you think that oxygen would be larger than nitrogen. Let's look at them both here in the periodic table. And so let's dig a little bit deeper as to why that happens. Even though there is an added proton, as we proceed across the chart, that's true. Let's acknowledge that, which would increase the nuclear attraction. What's going on is the fourth p electron in oxygen is paired in the p orbital. Let's go look down below at the orbital notation, which you should have learned how to do earlier. The orbital notation for nitrogen is such that the S2 P3 electrons in the second energy level, the P electrons are in 3 separate orbitals. Some of you may have seen this in your textbooks or with your teachers. You might have been drawing the same thing but with arrows, up and down arrows. I happen to like the circles and the crosses. Either is fine. But if we look more carefully at oxygen, the S2 for oxygen is paired. But then, as oxygen's electrons are parked in the p orbital, 1, 2, 3, and it's p4, meaning that one of the p electrons must be paired. That adds to the repulsion between the p electrons, and that repulsion seems to offset that increased nuclear attraction, which we want to acknowledge. This repulsion raises the orbital energy, and the ionization energy required to remove that paired up p electron for oxygen will be lower. Let's take a look at the other blip, which happened in column 3. Why is it that boron is lower than for beryllium? I realize now that it says nitrogen here. This should say beryllium, as I've highlighted down below. Let's take a look. It's been corrected here. So why is it that boron is lower than beryllium if the general trend is increasing across the chart? This one requires that we have a phrase ready to talk to AP or tell your AP readers about, that the electron that's being removed in boron is in the p orbital. You should be able to tell that by looking at the periodic table and seeing boron's last electron is in the 2p orbital, whereas magnesium electron is, both of them, the valence electrons are in the 2s. And so what happens is the 2p orbital has less penetration inside the inner core, less near to the nucleus. We don't really want to say that the 2p orbital is much further away, but it doesn't penetrate. The 2p electron does not penetrate inside the inner core, whereas s electrons do, or 2s electrons. 3s electrons penetrate into the second and first inner core area. This less penetration of the p orbital makes the Coulombic attractive force on the p electron smaller, and therefore easier to remove, that 2p1 electron in boron rather than beryllium.